All right, moving on to the last functional example here. Now, at first glance, a little overwhelming. We have a bunch of crazy numbers, a bunch of data points. Some are negative, some are huge, but we're going to see how well we can do. Now, when looking at it, I really only see one easy point for us to plot, so we'll go ahead and do that. And we're going to have to use the table to help us figure out the rest of this graph. So when you look at the left-hand side, notice how the x values are extremely negative. So the further we go to the left, it looks like our y values are getting closer and closer to -2. So there's a little asymptote there that we might have to be aware of. The further we go to the left, the closer we get to -2. So I'm just going to put a horizontal asymptote at that spot. Notice how this is just telling us about the left-hand side. You don't necessarily have to put the asymptote all the way through because it might not be the same case over here. We'll get to there eventually, but I'm just saying that this left-hand side is only telling us about this spot. Now, if we do take a look at the right-hand side, notice how the x values are getting very, very large. So the further we go to the right, notice how the the y values are getting closer and closer to -2. So since this end behavior on the left-hand side was the same as the end behavior on the right, we might be able to assume that there's a horizontal asymptote all the way through. Now let's take a look at some other things here. Notice how on the left-hand side, the y values are greater than -2. So that must mean your graph is above that asymptote. Very similarly, on the right-hand side, these values are less than -2, so your graph must be below the asymptote. Okay, so we're using the table of values, we're using the numerical information to help us draw a picture, get a graphical example. Some other things that we might have to be aware of is that we have no graph at -3 and we have no graph at the x value of 1. So, like I stated before when we had that square root example, undefined can mean many different things. It could mean that we have literally no graph there. It could mean that we have a hole there. It could mean we have an asymptote. So we have to pay attention to what the other data points are telling us. So at this spot of -3, notice how a little bit before that we're like -1.25, and a little bit after that we're also really, really close to -1.25. So we don't have anything going on at -3, but we are extremely close to the same y value on either side. So if you can picture that in your head, you have nothing going on at some point, but the left-hand side and the right-hand side are extremely close together. Notice how that's going to develop a hole in your graph. So we must have a hole at the x value of -3, and it's going to be roughly around -1.25 because that's where the left and the right side are meeting. So it might be a little difficult for me to draw a hole here because my pen is a little thick, but hopefully you can draw it more accurately on your paper so that we have a hole at -3. Let's go ahead and continue to play connect the dots. And then we somehow get, again, we are undefined, but we have to take a look at what the table is telling us. If you look at the left-hand side, we are close to a positive 3,000, where on the right-hand side, we are close to a negative 3,000. So in this particular case, notice how the left and the right side are not matching up. So there's no way we could have a hole at this x value of 1 because the left and the right side would not be meeting. So the only way that we could possibly draw this characteristic is we are going extremely positive on the left-hand side, but extremely negative on the right-hand side. And by doing so, that's creating a vertical asymptote. So this one's a little difficult because we have a lot of information going on here, but we're going to pay close attention to what the table of values is telling us about this graph. Hopefully, now that we have a picture, we can identify this as a rational function. And rational functions by nature are fraction equations. So just kind of jumping the gun here, we should have an equation that's a fraction in order to develop this graph. If we tackle some of the properties, domain and range, the shape of this graph again can change depending where the asymptotes or holes are located. So we'll go ahead and say changing for both the domain and range, but we will take the time to practice what it is in this case. So if we drag our pencil left to right, notice how we can go to the left forever. As we drag our pencil, we have to skip over the hole because there's no graph there to touch, and that hole happens at -3. We still have more graph to drag through, so we'll write in that U for union. We're going to write another interval. We're going to pick up at that -3 that we left off at for that hole. And as we continue to drag across, we hit kind of a barrier here at that asymptote at 1. But again, we still have more graph to cover. Our last interval, picking up at 1, and we go all the way towards positive infinity at the end. The range is going to be very similar. We're just going low to high. Notice how our pen can start at the very bottom. As we drag our pencil up, we initially encounter that horizontal asymptote at -2 that we'd have to skip over. We still have more graph to trace over, but notice how very, very closely we immediately hit that hole that we had, which has a y value. Okay, we were able to determine that was roughly -1.25. And after that hole, we still have some graph that continues forever upwards. So we'll go from -1.25 to infinity. All right. Now you might not have a hole in every rational function. You definitely will have asymptotes. So we can say perhaps always asymptotes, maybe holes. Holes are also referred to more mathematically speaking as removable discontinuities, and you'll see why when we get to the equation. All right, let's check out the equation. So in terms of figuring out what on earth this equation would look like, we're going to utilize those undefined spots to help us out. Now, since rational equations are fractions, we know fractions are undefined when the denominator equals 0. So we're going to use those undefined spots to help us write when the denominator would be 0. If we have an undefined location at -3, the related factor would be +3. And very similarly, if we are undefined at 1, the related factor would be -1. So that's a good start, I would say, with those undefined locations. We know that those factors would be in the denominator because that's when a fraction is undefined, when the denominator is 0. Now, determining about these holes and asymptotes, holes are commonly referred to as removable discontinuities because the factor in the equation would be able to be canceled out, aka removed. So if this x plus 3 was related to the x value of -3 that gave us the hole, we would need an additional factor of x plus 3 in the numerator. That way these would cancel out, aka be removed. So this is what is developing or creating that hole in your graph when you have those factors that are able to be removed. Asymptotes, on the other hand, are non-removable, so that means the x minus 1 is the only factor found in the denominator. We do not have to write an x minus 1 up top. Now, we can have other factors up top. Those are specifically found by looking at some x-intercepts. We can perhaps deduce that there's an x-intercept at the x value of -1, but again, this is just a rough sketch that we did. We would have to be more specific based off the table of values, and there is not an x-intercept given to us because notice how we do not have a y value of 0. So there is most likely another factor that we could possibly write in here. If it was exactly at that x value of -1, this would be an x plus 1, but we're not exactly sure if that's the case, because again, this was just roughly drawn, and it's not exact based off that table of values. So we can go ahead and just say, to the best of our ability, this is what we have so far for the function of n of x.